Hello, welcome back to the channel. I'm Savalian. Sav is fine too. If you're wondering where I've been, it's a long story, but the TLDR is that I was overworked, slowly perishing in a software chaos pit, beaten down by AI for a while. But it's okay because I got laid off a few weeks ago, so now I don't have to do that anymore. I am in a period of uncertainty right now, but I have a lot more time to do YouTube, so I've been trying to do some things here to see if anything pops off. I might make a proper life update video at some point, but honestly my plan was just to start making videos again and hope nobody noticed that I was kind of gone for a year, with the exception of some game VODs going up. I will do some more of those. I have some good games I've been streaming on Twitch that I want to get the playthroughs of up here, so look forward to those. But today's video, we're diving into Godot. We're going to talk about making shaders specifically for 3D, or spatial shaders as Godot calls them. But a lot of the information here is just generally about graphics rendering, so a lot of this will apply to other engines, other shader systems. It's just kind of how it works, underneath the hood. So step one, what exactly is a shader? And I don't have a fun graphic to show you for this, I just have Godot open, but I'll talk you through this and then we'll get started with a little hands-on demonstration. Shaders are basically the instructions that tell the GPU how information should be rendered to the screen. And if you think that you have never used shaders before, you actually are still using them. If you've rendered anything like 3D objects like this, you just think you haven't because modern engines have built-in default shaders. Blender has a default shader that you can tweak if you would like to. Everything that renders 3D like this has something built in nowadays, so you don't need to write them from scratch like I had to do in college. So in Godot, for example, Unity is similar. The default material that it applies to a mesh in a mesh instance 3D uses a shader where the instructions basically say, with the list of vertices from this object, draw them where they belong in 3D space based on the camera position, don't do any additional processing, and just make them a gray base color with simple lighting applied. And what the shader actually does behind the scenes to go from 3D mesh coordinates to this rendered image on screen is somewhat complicated if you don't have a background in graphics programming, and I'm not going to go into any of that because frankly you don't need to know it anymore. Some of it might be useful as background information to inform your shader work in the future, but if you're just starting, you don't need to worry about all the math that's happening behind the scenes to make this image work the way it does. But essentially, because objects are modeled with this 3D coordinate system, but the screen it's rendered to is basically a 2D plane, it does math basically to convert the points in 3D into 2D with the viewport or the camera settings that you give it. There are also different ways to apply lighting to an object that all require slightly different math, and lighting is even getting more complex as graphics programming advances. Things like ray tracing and global illumination were not really feasible, at least not in real time, 20 years ago. But lucky for you, like I said, the engine does a lot of this for us, so you don't need to understand the math behind a certain lighting technique or the mathematical difference between rendering an orthographic or a perspective view, because we have our beautiful modern engines. In most cases, we really only need to mess with custom shaders if we want to do something special. And it's kind of fun. Shaders are a lot of fun actually. But let's get started here. So I've created a new scene in this little test project that I just use for prototyping stuff. I've added a mesh instance 3D here with the donut, a default mesh donut. This got the default material when I loaded it in, but I have also added a shader, which is down here in the shader node editor. Don't look at my other stuff, that was a different project. And then I've also added the shader, where is it? Shader material. In order to apply your own custom shader to a material in Godot, you need the shader material resource, and then you can just drag it right in here. And then if your shader has any like parameters, they'll show up in here. We're not going to cover shader parameters today. I think I did talk about them in a previous video, my fish shader, because I worked with them quite a bit in there. But for now, we're going to kind of go through the basics, the simple basics, just get a feel for what shaders do and how they do it and how you can start to build your own thing with shaders. And I've also just added a simple camera and a light. So I've got my material applied to my donut here, and we can open the shader editor. I am going to be using the visual like node editor that they have because it's just easy for my brain to wrap around when it's in the flowchart like this. And I feel like it's also easier to explain. Technically speaking, you can write shader code that does all the things we're going to do today, but I never bothered to learn Godot's shader language. I barely knew like OpenGL shader language when I was working with like shaders back at college, and this is just easier for me. I think there's probably a couple things that you can't do with the shader editor, but I haven't run into them. I'm expecting that they're probably highly specific. And then there are also nodes. Oh gosh, I forgot what it was called. Is it under special? Expression? Okay, yeah, so expression, you can just put shader code in here if you need something that is highly specific and you have like code for it, for example. You can still use that in this visual editor. So we're just going to use this, and we're not going to worry about writing shader code by hand because I don't want to. Now, the first thing I want to point out is that a shader resource in Godot is actually 2 shaders, or technically 3, I think, if I'm reading this correctly, but the ones I'm familiar with, vertex shader, fragment shader, and these typically work together. So the vertex shader is the starting point, so to speak, and this is what determines where the vertices are in the scene. So things like where the camera is, how the global coordinate system maps to the 2D coordinates of the camera. And then it also outputs things like normals, things like UVs, which is how we map textures to objects, vertex color, things like that. So step 1 is determining the sort of form of it, the shape of it, the vertices of it. So the vertex shader takes in all the raw coordinates and information from your like mesh object, essentially, and then it processes them somehow, sends them out. Here's our output. And then they go into the fragment shader, and this essentially renders the pixels. So we have a lot more things in here, and all of these things are related to like the visual surface of the object. So we have albedo, which is kind of just like a fancy word for the color of it. Alpha is like transparency, metallic roughness, specular emission, ambient occlusion, normals. I don't know as much about this other stuff. I probably should learn. But these are kind of the basic things that will make your thing look like something on screen are all coming out of here. And I think most of the time you're going to be living in the fragment shader. Most examples of custom shaders work with the stuff that's in here and not as much in the vertex shader. But we are going to talk about both in this one. I'm going to go kind of as quick as I can and try not to ramble too much. So even though it's not super common to actually do vertex shader stuff, in my experience, I'm sure there's a lot of people who do work with the vertex shader. We are gonna play around in here and just see what we can do and how this shader stuff all works. So the first thing we want is some kind of input, right? Because we have this output. Things are getting sent to this shader, but we're not using them at the moment. So in here we can look at all these. I'll make this a bit bigger. Oh, I've just realized that this pop-up doesn't show up in my capture. You can't see this. Okay, well, when you do this, right click or click add node or something like that, you will see like a bunch of expandable sections for different kinds of nodes that you can put into your shader here. I've gone to the input section. There's 3 sections in there, all common and vertex. And what I want to look at here is mostly the vertex input. This is kind of the vertex information that's coming into the shader. We have things like color, we have things like tangent, the vertex, which is the position of it. We have some positions, the node position, the camera direction. We have a lot of things in here, and all of them have a little like tag next to them for what type of data they are. And this is important to look at because the way we're going to hook these up, it's important that we understand like this is a vector with 3 points in it. This is a vector with 4 points in it. This is just a float. It's just a number, things like that. It's a bummer that you can't see these, but I'll talk through them as well as I can. I'm going to pick vertex, which is just the coordinate of the vertex. And then now you can see it's come in here. It's an input node. I'll zoom in. And then if I want to look at the individual pieces here, there's a little drop down right next to it. It says red, green, and blue. I would typically mark these XYZ because this is the position of the vertex. If I want to, now that I have this input node in, I can do this drop down. You can't see the drop down in the capture either, but it just opens up all the input types again. If I want to change this to a different, like I can change it to whatever exposure is. I'm not sure about that one. Time, I know this one. Color, I understand this one, but we're going to put it back to vertex. And then this little vec3 is the tag I was talking about. It tells you this is a vector with 3 points in it, just like we're seeing here. And then every time we're working with nodes in this, if we click on these little dots, we can drag out a line, and then we can hook these up to inputs of other ones. So if we just want to send this right back out, this is probably what it does already, honestly. We can just hook it right up there. We can disconnect by pulling on that. And then I think also if we try to hook something like this, where this is a number, this is just the like X value of the vertex position. I believe what it does if we hook it to a vector 3 is that it just puts the same number in all of those XYZ points. So this would just take the X value and put it in for all 3. And it's funny because of what has happened here. We can no longer see our donut because we're just sending all of this out to the same point. And that's also an example of how, unless we put something in the output here, it doesn't do anything to our model. Like we could have 1,000 nodes in this part of the little screen here, but until we hook something up to the output, it will not actually output anything. So the goal is to go from input, do whatever processing we need to on those values, and send the appropriate values to the output. It's kind of like a little game, you know? So I've got my vertex position as an input. I'm going to add a few nodes here. And as you're adding the nodes, you can look at the description of what you're doing. If you're not quite sure how it works, Godot also has pretty good documentation. There's not like a ton of examples in the documentation, but the documentation itself is pretty descriptive about what stuff does. And then there's a number of ways to add nodes. Like I said, there's a button up here. You can right click, add node, or you can also just sort of drag this and drop it, and it will bring up the add node thing that you unfortunately can't see in the capture. So first, actually, I'm not going to connect this to anything just yet. I'm going to add a float constant, and this is just going to be a number that we can set in here and hook up. It's kind of like a hard-coded input value, if you want to think about it that way. And then I'm going to drag this, create a node, and I'm just going to do add. And I want to add this to a vector 3. So I'm going to choose the vector 3 add option. If you type add into the create menu, you'll see a whole bunch. You'll see like a float add, an int add, a uint add, I think is what that says. It's kind of small. You'll also see multiply add. I'm not totally sure what the use case is for that. I'm sure it has one if it's common enough to be like a special option in here. But I'm just going to pick vector 3 add, and then it's going to put my float right in there. And then if I take the position of this, the top one, which includes all X, Y, and Z, we add these together. Now, if I put this right into the vertex out, what does it do? Nothing, because the float is set to 0. If I set this to 2, oh, look, everything has moved. This is because we're just adding 2 to all the values. So if I do this to like 0.5, we're still in range. If I set back to 0, we're at the position that we started at. So you can see for every vertex that comes into the shader, we are adding this to it and then sending that position out. We can also do negative numbers, subtract. And because we're doing it to all 3 of the values, it's going kind of like diagonal ways in the coordinate system here. Well, that's basically all we're doing with shaders ever. Everything in the shader is really just numbers, you know? Positions are numbers, colors are also numbers. Technically speaking, UVs getting a specific pixel and applying it, also numbers. We're going to talk more about what it exactly means for colors to be numbers as we get into the fragment shader stuff. But for now, start to shift your thinking, taking numbers as an input, whether the number is a position, a color, and we're going to just do some math on those numbers. Now, most of the time it's fairly simple math. You don't need to be scared. If you, for some reason, need to like build a vector out of individual floats, there is also a node called compose. It has like vector 2 compose, vector 3 compose, vector 4 compose, where you can, for example, if I just want to add, if I only want to add the X value, which would be red, the first one, we can just add these and then put that into the X value, bring over the Y and the Z, and then put that out. It only moves in the X direction. So we have like negative 2. We see X is the red line here. Positive 2. See how that works? And then we actually aren't using this. We could delete it if we want to. In fact, I think I will. Whenever you're making the shaders, try to think through what you're doing. And that's why I like the visual graph. I feel like it's so much easier to visualize what's happening when you have these things connected together instead of just trying to keep code straight in your head only. In fact, when I write code, sometimes I will make like a little chart to help myself remember like, okay, this value is going here and we're doing this. The shader editor makes that easier. Now to bring in some fun, the time variable. If you check the Godot documentation, which is a good idea just in general, it will explain to you that let's see, it doesn't have that here in the node creation description. It's actually maybe a little too simple in there, but in the documentation that they have on their website, this explains that this is the number of seconds since the engine started running, and then at 3600 it starts over at 0. So it loops after 3600 seconds. I don't know how many minutes that is. A lot of minutes, maybe an hour. But because we know math, we're smart. I know that if we want it to repeat every certain number of seconds, we can use a modulus operator. Now, we don't have modulus as under that name in the node section here, but we do have remainder. So if I'll take a float remainder, since time is a float, and we'll just put another constant in here just to make it easier to change things. I don't have to click into these little tiny squares. So we put time in the top here, our constant in here, let's say 3 seconds. So what this is actually going to do in terms of math is going to divide time by 3 and then send through the remainder. So this value is always going to be between 0 and 3. Now taking that value, let's multiply it. We have multiply here as well. I'll just do a float multiply. We're going to scoot everything over a little bit. We're going to multiply it by our constant here and then put that into the add. Now let's set this to an actual value and look. So can we understand what's happening? Are we getting the hang of this a little bit? positions of the vertices in the object, we have our float constant, we have time, which is increasing, which is what's creating this movement, and then we have this remainder. We're going in here, we're essentially clamping this value between 0 and 3, and then we're multiplying it by this. And what happens when you multiply a number by 0? It is 0. If you multiply it by 1, it's whatever the number was. As we multiply it by 2, it's 4, So as the time is going up, this multiple is going up, the number's going up, and then it's getting reset to 0. It's all going back down. Does that all make sense? I hope it does, because we're moving on. As the last thing, we can also apply colors to vertices. We can put a color on a vertex. You can also do this in a 3D modeling software like Blender. Obviously, this default donut does not have any colors applied. It's just this plain like white gray donuts. I guess it looks more gray when there's no light on it. So if I create a color constant, this is where we see, just like everything else, color is just numbers. This is a vector 4 where the first number is for the red, the second number is for the green, the third number is for the blue, and the fourth number is for the alpha or the transparency, the opacity, whatever you want to call it. And then as a whole, we combine this, we get a color with an associated transparency value to it. So I'm just going to leave this as white for now. If you want, you can click on this. It brings up another little pop-up that you cannot see in the capture, or you can set the color value. I'm just going to leave it at white for now, which is 1, 1, 1, 1. That's basically each of these numbers goes from 0 to 1, and white is full ones, assuming it's fully opaque, fully visible. Black is all zeros, and typically the alpha will be 1 unless it's a transparent black, which then it would be all zeros. So if I set red to 1, but green and blue to 0, like that, obviously we get red. It's full red, it's nothing else. And then if we do something like, let's add like half green, now we have this like orangey color. So it's all just math. It's all just math. Numbers combining, multiplying, adding, subtracting. That's all we're doing in the shaders. So I'll put this back to white. So now just to make it do something fun, we're going to take the red value of this and just do like a float multiply. We're going to multiply it by the z value of the position of the vertex. And then we'll just send that color out. The keen-eyed among you will notice that nothing has actually happened here. We have not actually changed any colors here, and the reason for that is because the fragment shader is not doing anything with this output. By default, the position is getting utilized in the fragment shader, but the vertex color is not. Typically, you use things like the albedo output here. They don't incorporate vertex colors by default in the fragment shader. So what we need to do to actually see something is pull in an input, and then it's just called color. It's under input fragment color. Bring that in. Sorry, I know you can't see the create node menu. I didn't even consider that. Now, if we just take this directly from the input and we put it in the albedo, look, isn't that beautiful? So what's happening here? Why is just half of this donut black? Well, that's because right here, where the line is, that's between 0. It's between the positive and negative on the z axis. Couldn't remember the word there. And because we're not recomposing this into a color, it's taking this red value and then it's just creating a new vector 4 where all the values are that red value. If I do want to compose this, we could do vector 4 compose. We could put red in there, and then we can just carry over green, blue, alpha, take this color and send it out. Then we get blue. Now why is that? It's because white has all of these values at 1, But if the red is at 0 and green and blue are both still at 1 because they're not being impacted by this, they're the only color that's left, mathematically speaking. So when you combine full green and full blue, you get this cyan color. Very pretty. If I change this color value so that it is mostly red, we do see kind of a fun, it's actually kind of my colors a little bit. I guess it's a little too teal, but the pink and the blue. So on this side we have the color that we're putting in, and then on the other side we have that same color minus all the red, because on that side we're multiplying it by 0. If I want to do something slightly different, we can take maybe the green, which is the Y, it's the up and down axis, and then it's kind of hard to see from this angle, but it's getting the same treatment but up and down. And you'll also notice that the donut has been tilted in the scene a little bit. I just did this to make it fit in the camera view better. But the coordinates it's using for this operation are not dependent on the world coordinates. They're dependent on the actual mesh coordinates. So every mesh has its own origin, its own 0, 0, 0 point. Usually it's like in the middle of the object or in the middle bottom of the object. It depends on how the model is made. But we can see that it's probably like right here somewhere, right in the middle of the donut, because we're getting cut off right there. Now there are ways to get the world position, which we're going to play with a little bit later. But for now, this vertex coordinate is local to the object. And just like a note on vertex colors, the vertex colors are limited by how many vertices there are in a particular mesh. So for example, this one's probably got, you know, several loops around this donut. It's got like a decent amount of vertices to create this smooth circle shape. But if we wanted to do something like apply a photorealistic image, you know, like a texture to the surface of this, there simply would not be enough vertices to make that image realistic if we were setting the color of each one to a certain value to match the image. And that's why we have UV coordinates, and it's also why all the texture stuff that we do happens in the fragment shader. That may not make like a ton of sense right now, but it's one of the reasons why, even though technically you can set vertex colors in the vertex shader, it's not usually the way that people do apply colors to objects when they're writing shaders like this. Okay, so now I'm gonna delete all this. We don't need all that. We're gonna move over into the fragment shader, where we're gonna spend the rest of this video, which I hope is not gonna be an hour long. It might be an hour long, I'm sorry. Hopefully it's at least useful if it gets that long. I'm gonna delete this as well. We're starting fresh. Okay, so first you'll notice there are a lot more options here for outputs, and a good portion of these outputs are available to set in the standard material directly. And the reason for that is because this shader that we're using here, the default building brick that we're building on top of, is the same thing as the default material, the standard material. So if I go here, we can see we have the albedo here, we have roughness, metallic, emission, rim, clear coat, whatever the hell this is. We have a lot of the same options here. Additional like parameters and stuff are available in the standard material, so they have exposed a lot of this stuff directly to the user. But we know from this that this is a physically based rendering based. This shader is so based, you guys. Is that what the kids say these days? Anyway, this is built on like a physically based rendering system, so things like metallic and roughness have been tuned so that they make things look metal or rough or smooth or non-metal, depending on the values, in a semi-realistic way. Once again, you don't need to know all the very specific parameters for tuning your shader to render metals just the way that you want them to, because a lot of that work has been done already and provided here in Godot. So I'm just going to add a couple of floats here just to show you what I mean. If we hook these up to the roughness and the metal, we have, let's see, roughness is set to 0, so it's smooth. And then if we set the metal to 1, we've got an extremely metallic, extremely smooth object here. If I move this around, we can see the effect of the reflections there. But, and it kind of looks like it's disappearing into the background just because the skybox is reflecting off of it. If I make this, let's see, less metallic, but still very smooth. That's what we got there. And honestly, it's a good idea to just play with the settings for these PBR shaders. See what creates a look that you like before you get into building your own shaders, because it's going to give you an idea of like the numbers that need to go in here in order to achieve certain effects. Because remember, everything is numbers. If you can find the way to calculate the numbers to your satisfaction, you've made your shader. That's it. That's all it is. And then kind of obvious, but I don't think I've specifically called it out, is that if we don't connect an output to one of these, it will just use the default value. So right now, the default for the standard shader is 0 metallic, and I think either 1 or 0.5 roughness. Let's check. 1 roughness. Okay, so it's a very rough, non-metallic object by default. So if we want to change that, we will have to send something to these values, because otherwise it's just going to use whatever the default settings are here. And that's the same for all these other ones. So like albedo is just going to be this like whitish grayish color. Normals are going to be directly from the vertices probably, which is good for us because we don't want to have to define everything manually for all these different options. Especially if we aren't doing anything different with them anyway. Now, if I do a very similar thing to what I did in the vertex shader, and we want to change the colors of these things based on position, what we can also do is incorporate this node position world input. Now, this is the position of the entire donut. So like right here where the origin is, wherever this position is at is what's going to be used for this value. And then let's add another color constant, and then I'll put in, I don't know, like a purple color. Let's see how that goes. And then just like exactly like we did before, let's pull out the X position, multiply it by the color. We'll multiply it by just the red of the color, and then we'll compose it back into a vector 4, and then send this out the albedo. So we see the entire donut is blue. If I move it in the X position, we start to see that changing. We're getting closer to this purple color. And also, if I just keep moving this donut over and over, you'll see it's getting like visibly shiny. Now, why is this happening? Now, this is because, again, remember, colors are numbers. And the number for the red in this color is just getting multiplied by bigger and bigger X values. So this red here is probably like 8 or 10. So we have an 8 or a 10 in the red value, but the color should only go from 0 to 1. So this is how the current rendering settings, I believe this is an HDR thing. I'm not totally sure. Don't ask me to explain HDR to you. That's not my specialty, but what we can do if we don't want this to happen, if we have some math like this that could result in the color going lower than 0 or greater than 1, what we can do is we can clamp it, vector 4 clamp. The default parameters already clamp it between 0 and 1. Perfect. We can put that right there. And then we don't get this increasing intensity of red on our donut, but we do still get the transition from blue to purple. And you'll notice that it's the entire donut changing as it changes position. And this, once again, is because the position, node position world, refers to the position of the entire node or the entire object here. if we want a smooth transition, we can still get the vertex position as an input. And what we can do here is actually add these vertex 3. So we have the origin, and then this is, remember, the vertex's position relative to the object's origin. So we just add these two, boop and boop. And then we can pull the X value from here, replace this one there, and then we get a smooth transition based on the X position of individual vertices, but this is in the world and it's not just within the donut object itself. And you can use this like if you have anything where you want to like maybe color a terrain by its altitude, you could do that. There's a lot of things you could potentially do with something like this where it's based on world position. That's just the example that came to mind. So now we have a grasp on how we get these numbers into the shader, how we do things with them. We can add them, we can multiply them, we can take the numbers apart, put them back together. But there are still like some pretty common things that I've seen people do with custom shaders that I want to talk about that you may never use, you may use it frequently, just depending on what you're trying to do. But there are a couple of like special nodes that I see used very frequently that it would be good to understand what they do. And the first one is called Fresnel. Fresnel? I'm not totally sure how to pronounce it, if I'm honest. We can see here though, typically you would need to pass in some things to facilitate the math. Godot has these set by default, the normal in the view. And then we have some parameters here that we can change and see how it works. But basically what the Fresnel value does, the particular point that it's rendering, so like as it runs through all these pixels, these fragments, how close that thing is to being perpendicular with the view, it returns a 1. So it's kind of hard to explain, but the short version is it finds the edges of what you're looking at. And if I just drop this value directly into the color, you can see immediately what I mean. So like here, around the edge, we have our lightest white. And then the stuff that's facing sort of directly towards us is a black. So the things aligned with our view are black. The things that are perpendicular to our view are white. Or the things in the sort of in the middle here are like a gray color. So what this is frequently used for is for outlines, finding edges for certain things. There's a lot of sort of neat visual effects you can create with something like this. So that's what that's for. And just to take it a step further, we're gonna add a step node. And this is another node that is frequently used for a lot of things. This kind of behaves like an if statement for shader code. I think Godot added an if node. This is kind of unusual for shaders from my memory. I don't know if other shader languages have like a proper if statement, because for a while the step node was kind of how you do it. And what this does, and I can sort of read the little blurb here, return 0 if x is smaller than edge, and otherwise it's 1. So if we plug in this Fresnel value into x, and then we set the edge to, let's say, 0.5. Now let's think about what this is going to do. So the parts of this that are black, we know the color is close to 0. So black is close to 0, white is close to 1. So anything that is below a 0.5 or below like a medium gray is gonna get set to 0. And anything above that that's closer to white is gonna get set to 1. So instead of this like fading between white and black, we're gonna get a hard edge. Like that. So now we have like a pretty crisp outline. as I move this, you'll see that the outline changes. If we want it to be much more crisp, we can set this threshold even lower. So we do 0.25, or no, sorry, higher, 0.8. So this means it has to be really close to white before it gets set to white. Everything else gets set to black. So let's set this to like maybe a 0.75, maybe a 0.7. There we go. Oh, I keep misclicking on my my little widgets here. Gadgets, gizmos, what do you call these? Okay, well let's put it like that. So we have the Fresnel, a value based on how close something is to a perpendicular edge. We have the step, which can be used in a lot of ways. There's a lot of really clever ways to use the step to create certain looks. This is just one way. It's a pretty common way that I've seen. And now, what if we want to incorporate the colors again? We have all this color based on vertex position. Let's think about how can we combine these colors together? Think about the numbers, think about the math. We have this vector 4 with the color values in it from 0 to 1. And then we have this section here where all the numbers are either 0 or 1. And let's think about, again, you know, if we multiply a color, a number, by 0, it is 0. Otherwise, if we multiply it by 1, it's going to be whatever the number was. So that's exactly what we need to do to combine the color with specifically the white portion of this output here. So we bring this color in here. We bring our Fresnel outline here. Put this in here. There we go. Look at that. We've multiplied all of this technically, but only the white results in an actual number. The black stays black because 0 multiplied by 0 is 0. Now, this is fine, but what if we don't want the donut to be all black like this? What if we want the middle of the donut to be a color? This is where we cover how you don't need to only use these outputs for one thing. You can use them for two things. So I'm going to add another color constant. We're going to make this, I don't know, like a blue, like a dark blue. Okay, now we know we have the outline here. I want to target the opposite of that. So how do I get the opposite of that? We don't multiply this by -1. That might be kind of what you think of immediately. Actually, what we want is a 1 minus. So think about this. 1 minus 1, or 1 minus the white portion, is going to be 0. But then 1 minus 0, which is the black portion, is going to still be 1. So this is going to swap all of our blacks to whites and all of our whites to blacks. If we then multiply this, just like we did with the other one, this one is going to be, guess, blue with the outline being black. Now, I think you can probably figure this one out. How do you combine these ones? We don't want to do a multiply here because the black is just going to stay black. It's going to make the whole donut black. But if we add the black portions, still 0, are going to just be added to the non-black portions of this one, which are, you know, whatever the color value is in that point, closer to 1 than 0, and with the colors that we've selected. And then on this other one, remember this one has black on the middle, this 0 value is going to be added to the blue that's in this one. So that's exactly what we want. We add these two together, and we get blue in the middle, our outline on the side. There we go. And all of our other stuff is still functioning. All of this vertex position stuff is still functioning. But there you go. That's how you build shaders. One step at a time, one piece at a time. You can always, like I was doing, you can always take one node and output it and see what it looks like if you're getting closer to your vision, if you're getting farther away from the vision and need to reroute. You can always do that. There are little like previews on these. I'll be honest, I actually don't know how to turn this value into something useful for debugging. I'm sure there's a way for people who have worked with the Godot shader editor more than me. You may know how you set like a test object or something for these little previews. But for now, this is typically how I work. I usually set up an object in a scene on its own with lighting that is similar to the lighting that would be in like the final place I want to use it, and I just build things out piece by piece. And the benefit of understanding how these nodes work, what they do, what happens to the numbers as they transition between these, is that you will be able to follow along better with like a tutorial for a very specific type of shader, even if it's not made in Godot. Like all this stuff, the step function, the Fresnel calculations, various types of inputs, you know, doing operations on vectors, all of this stuff is completely compatible, you know, like with all of the ways of creating shaders. So if you are familiar with like how code is structured, you can probably follow a code-based shader tutorial. But gosh, I hope this video doesn't turn out as long as it looks right now in the recording, but even though it's been, for me, like an hour and a half, there's still so much more we could talk about with shaders, but we just speed ran Shaders 101 and need to take a little breather. These basics should be enough to get you going, but let me know what you would like to see next. If there's a specific type of shader you'd like to see a tutorial on, if it's something I'm familiar with, I could probably do one of those. We could also talk about UV coordinates and textures, which I didn't really have time to cover here, but are a pretty big portion of building shaders in most cases. We could also talk about parameters, either like shader parameters or instance parameters. I know I've talked about them briefly for my fishing game videos, but I could talk about them a little bit more specifically and directly in a video about like how to set them up, how to use them. So just let me know what you would like to see. I've made a lot of shaders in my time, but I feel like most of them are highly specific, like the previously mentioned fish shader. But let me know if there's anything you'd like to see. Thanks for watching. Don't forget to subscribe. It's good to be back. Peace. See ya. Bye. I'll hopefully be back sooner than a year. Okay. Goodbye, everybody.